Bismillahirrahmanirrahim. Hello, dear students. I hope you are having a nice day. I welcome you all in class of Real Analysis by Robert G. Bartle. I am Azmat Ali. We are discussing exercise 2.1. In the last lectures, we discussed up to question number 19. In today's lecture, we will start from question number 20. In this short lecture, we will discuss three questions, question number 20 to question number 22, and you will enjoy today's lecture. I will discuss the different alternative method to solve the same question, and inshallah you will enjoy from these methods. Question number 20 has a statement. It has the two parts A and B. In the first part, we have to show if C is any, this is C. If C is any real number that lies between 0 and 1, we have to show that C square is 0 less than C square and C square is less than C and C is less than 1. Actually, in fact, for any real number that lies between 0 and 1, whenever you take its higher power will be less than its smaller power. For example, if I choose C is equal to 0.5, that belong to the interval 0 to 1. Now, if you take its square, then its square is 0.25. You can notice that C square is less than C. So here we will show that C square is less than C and C is less than 1. Further, in the B part, we have to show if 1 is less than C, that is C is greater than 1, then 1 is less than C and C is less than C square. Now, in this case, when C is greater than 1, that is clearly C is positive. In this case, the higher power will be greater than the smaller power. So, firstly, we prove its first part. This is very simple. It is given that our C lies between 0 and 1. So, it clear that C is positive. So, multiply this inequality number 1 by C greater than 0. So, when you multiply this inequality by C greater than 0, it will not change the sign of the inequality. So, we have 0 less than C square less than C. Say this is inequality number 2, combining inequality number 1 and inequality number 2, we have 0 less than C square less than C, and C is less than 1, which is required to prove. In the second part, B part, it is given that 1 less than C, it means C is clearly greater than 0. So, multiply 3 by C positive, we have C into 1 C and C into C, this is C square. Say this inequality number 4. Combining 3 and 4, we have 1 less than C less than C square, which is required. Question number 21, this is very interesting and the basic question. Prove that there is a no natural number n such that that lies between 0 and 1. You know, by the definition of natural number, all natural numbers start from 1, 2, 3 up to so on. In this question, we have to show that there is a no natural number between 0 and 1. And further, in the B part, we have to show that there is a no natural number which is even and odd both at the same time. So, firstly, to prove that there is a no natural number between 0 and 1, we suppose on the contrary there is a natural number n such that it lies in this interval 0 and 1. So, let there is a set S that consists on all those natural numbers that lies between 0 and 1. So, if S is non-empty, then well-ordering property of n or well-ordering principle which says that every non-empty set of positive integer has a least element. So, if S is non-empty and we are assuming that S is a set of all positive natural number that lies between this 0 and 1. So, it means there exists a least element m belong to S. However, if m is an element of S, so m will satisfy this condition that this set consists on all those elements that lies between 0 and 1. So, clearly our m will also lies between 0 and 1. Multiply m on both sides, we have 0 less than m square, m less than m less than 1, that we have proved in above question. This implies 0 less than m square less than 1. it means m square is also an element of S, because in S all those elements uh, exist that lies between 0 and 1. So here m square is also lies between 0 and 1. This implies m square is an element of S. This shows that m square is also an element of S and smaller than m, because from this inequality you can see that m square is less than m. So this contradict with the fact that m is the least element, because above we have assumed that m was the least element, but now you are saying that m square is smaller than m. It means m is not a least element. Hence our assumption is wrong, that that it means there does not exist any natural number n such that 0 less than n less than 1. In the second part we have to show that there is a no natural number which is even and odd at the same time. We suppose on the contrary that there exists a natural number n such that it is even as well as odd at the same time. If it is even, then n can be written as 2k, and if it is odd, then it can be written as 2k plus 1. You know that this number 2k plus 1 is always odd integer, and 2k is always an even integer. So both are the form of n, and both are so they are equal. But from this equation, 2k is equal to 2k plus 1, by cancelling out or subtracting 2k on both sides, we have 0 is equal to 1, but this is not possible. Hence, there is a no such n belong to n exist. Mean to say, there is a no natural number exist which is even as well as odd at the same time. Question number 22. This is a very interesting question, and I have solved this question by using three different methods. In this question, there are two parts, A and B. In the first part, if C is greater than 1, then we have to show that Cn is greater than or equal to C for all natural number belong to n, and Cn is greater than C if n greater than 1. Mean to say, if n here n is equal to 1 is not included here. In question number 20, we have proved the same scenario, but in that question we have show C square is greater than C. Now here we have to prove in general that C raised to power n is greater than or equal to C. And similarly, if your C lies between 0 and 1, then we have to show that C raised to power n is less than or equal to C. And inequality hold when n is greater than 1. So method number 1, A part. Given that C is greater than 1, it means C is positive. Multiply 1 by C greater than 0 on both sides of 1, we have C square greater than C. Again, multiply 2 by C positive, we have C cube greater than C. So in this method, I will make a chain. Continuing this process, C raised to power n is greater than or equal to C raised to power n minus 1. This is the nth inequality, or you can name it by star or any or someone else. Combining all these inequality, we have C raised to power n is greater than C raised to power n minus 1. This is greater than n minus 2. This is greater than C cube, C square, C greater than 1. And this implies finally Cn is greater than C when n is greater than 1. But equality hold if n is equal to 1. If n is equal to 1 here, then C raised to power 1 is exactly equal to C. So C raised to power n is greater than or equal to C for all n belong to n. Because when you include n is equal to 1, now n is a natural number. This was the method number 1. Now I discuss method number 2, that is method of factorization. Given that C is greater than 1, consider I have to show that Cn is greater than C. So I am assuming the factor, considering the factor C raised to power n minus C. By taking C common, we have C raised to power n minus 1, and by using its factorization, C raised to power n minus 1 has a factorization C minus 1, C raised to power n minus 2, C raised to power n minus 2 up to some C plus 1. You can verify this formula by simple formula of cube. If we have C raised to power 3 minus 1, then you can write it as C raised to C minus 1, C square plus C plus 1. So generalizing this formula for power n minus 1, we can factor this formula by C minus 1, C raised to power n minus 2, which is 1 less than this complete power. I hope now you have understanding of this formula. Next, as C is greater than 1, this implies C minus 1 is greater than 0, and also If when c is greater than 1, it means any power of c is also positive. It means this sum is also positive. So each term of this formula is of this product is positive. This implies the left hand side cn minus c is positive. And finally we can say that c raised to power n is greater than c for all n greater than 1. uh, and equality hold if n is equal to 1. Hence cn greater than or equal to c is for every positive natural number. The method number 3, this is a very mature method. uh, in this method I will use the Bernoulli inequality. Given that c is greater than 1, this implies c minus 1 is greater than 0. Let this number c minus 1 is equal to x. This implies x is positive. So adding 1 on both sides, we have c is equal to 1 plus x. So this implies c raised to power n is equal to 1 plus x whole power n. So by using the Bernoulli inequality, we have the Bernoulli inequality says that 1 plus x whole power n is always greater than or equal to 1 plus nx, and 1 plus nx is always greater than or equal to 1 plus x, and 1 plus x is equal to c here. So this implies cn is greater than or equal to c for all natural numbers. Further, note in star equality hold if n is equal to 1. Otherwise, when n is greater than 1, then c raised to power n is greater than c only. If you take n is equal to 1 here, then these three expression will always equal. So in this case, we have the equality sign. Otherwise, c raised to power n is greater than c. Next, in the B part, we have 0 less than c, c less than 1, and now we have to show that c raised to power n is less than or equal to c. Okay, we can use both method number 1 and method number 2. Method number 1 was the method of chain, where I have made a chain, and method number 2 was the method of factorization. But we are using more sharp method here. I am not using method number 1 and method number 2, but you can use here. It is given that 0 less than c, c less than 1. Let us substitute b is equal to 1 over c. B is a real number which is equal to 1 over c reciprocal of c. As our c lies between 0 and 1, so whenever you take the reciprocal of any number between 0 and 1, it will be greater than 1. For example, if my c is 0.5, if I take 1 over c, this is 1 over 0.5, or 1 over 0.5, this is equal to 2, which is greater than 1. So I am supposing that b is equal to 1 over c. This shows that b is greater than 1. So if b is greater than 1, so then I can use the part number A. The part number A says that if c is greater than 1, then c raised to power n is greater than c by using Bernoulli inequality. So this shows that I can use the part A, and the part A says that for any real number which is greater than 1, its power n, b raised to power n, is always greater than or equal to b. There is no need to prove again the part number A here for b greater than 1. We will use we will give just its reference. So b raised to power n is greater than or equal to b. As b is 1 over c, so replacing the value of b is equal to 1 over c here, this implies 1 over c raised to power n is greater than or equal to 1 over c. By cross multiplication, we have c raised to power n is less than or equal to c. That is required to prove. So I hope today discussion is very helpful for you. If you find my lectures helpful, kindly like, share and subscribe. Inshallah, in the next lecture we will discuss from question number 23. See you in the next lecture. Take care. Allah Hafiz.